If you talk at people, let's say my age, if you talk about data fusion, they basically think about pan sharpening. The fact that you're basically using panchromatic imagery at very high spatial resolution in order to improve the multispectral imagery. Now, if you talk of data fusion, people start to think about machine learning or artificial intelligence, and the fact that you're using data from multiple sensors, not even sensor from satellite, but maybe social media or whatever. So it was completely different meaning.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. There have been a lot of advances in remote sensing over the years, but nowhere have the advances more significantly impacted our ability to process remote sensing data than in the development of machine learning. So today, we'll be going through a timeline, sort of a time series, of how machine learning techniques and applications have evolved over the past few decades. This episode of Down to Earth comes from the Image Analysis and Data Fusion Technical Committee of the Institute of Electrical and Electronics Engineers Geoscience and Remote Sensing Society. The Image Analysis and Data Fusion Technical Committee serves as a global multidisciplinary network for promoting theoretical advances and best practices in image analysis and data fusion. To learn more about this technical committee and how you can get involved, visit their website at grss-ieee.org/technical committees. I want to begin our first episode of Down to Earth Season 2 with a little remote sensing 101. So remote sensing in general terms is all about gathering information about an object or phenomenon without making physical contact. The first form of remote sensing was actually photography, and its first uses for Earth observation, so to speak, were military in origin. Fun fact, the earliest aerial photographs were taken between 1850 and 1860, when folks attached some cameras to tethered balloons. Today, the term remote sensing largely refers to the use of satellite or aircraft-based sensor technologies where we measure the physical properties of objects using electromagnetic energy. The origins of modern remote sensing stem from World War II, with the development of radar, sonar, and thermal infrared detection systems. With the declassification of early military systems came a boom of progress in remote sensing technology, and by 1964, we had sensors capable of operating in virtually all bands of the electromagnetic spectrum. Since then, the resolution and capability of existing sensors has only increased, as has the use of this data for decision-making. However, the advances in technology have resulted in a major challenge that scientists have been trying to tackle for years: how to process the increasing amounts of data being gathered through remote sensing. Today, we'll be speaking to 3 different scientists who will help us answer this question by tracing the evolution of machine learning in Earth observation. Let's jump in.
In high school, I wrote my first paper on remote sensing in the Science mag. And that was in, I think, 1978. And at that time, we were just looking at Landsat imagery with low resolution, 4 channels and so forth. And when I did my final project here as an undergraduate at the University of Iceland, I was also working with remote sensing Landsat imagery. So it was again low resolution, only 4 channels, red, green and blue, and near infrared. Maybe we can say the resolution was around 60 meters. And I was basically doing sort of basic image processing of Icelandic glaciers.
This is Dr. Jón Atli Benediktsson. He's currently the rector and president of the University of Iceland, and for over 30 years, he's been a professor of electrical and computer engineering. Since beginning his career in remote sensing, Jón has been fascinated by the applications of data. But it wasn't until his experiences at Purdue University's Laboratory for Applications of Remote Sensing, or LARS, that he found the perfect focus for his fascination. At LARS, he was tasked with 2 main responsibilities. The first was learning how to analyze and extract information from multiple sources of low-resolution data, and the second was to propose new approaches for multi-source data analysis. With his background in computer engineering, he began to consider how he could apply statistical models to the multi-source analysis challenge, which led him to a new and exciting field. So, Jan, when you first started your career, what kind of techniques were you using? And when did you start thinking about artificial intelligence?
Working on my master's thesis, it was mostly on analysis of multi-source remote sensing and geographic data and using statistical approaches. It was fine, but it was very limited because the data we were looking at were non-Gaussian by nature in terms of the topographic data sources. Then we had data where we could use Gaussian estimations or Gaussian probability distributions and so forth. And it meant that it was very incomplete. So in the 80s, we started looking more closely at AI approaches. And there was this neural network, we can say, groundbreaking idea of the backpropagation algorithm that came in the 80s. And I became involved in that fairly early on.
So, just to clarify for listeners, backpropagation is a fine tuning algorithm that was quick and easy to program. It was groundbreaking because it improved the accuracy of neural network outputs, making them more useful. So, going back, Jan, can you tell me more about these neural networks? What were they like and how did they change?
The neural networks in the old days, that I would say in the 50s and 60s, they were very, very simple and were not very useful for classifying nonlinear data. We can say the ideas were there, but the equipment and the algorithms and the data was primitive. What happened in the 80s, you got better algorithms and you got more computational power. The neural networks early on, they were used to learn from this database of facts and rules. That's basically an expert system. And when you had this expert system, that sort of gave you the solution. When I was at Purdue, I used to run my algorithms overnight, the neural network algorithms, and get the result in the morning. And sometimes it took days. But I was just looking at the data. I had maybe 7 channels, about 1,000 or 1,200 training samples. Nowadays, for data like that, this is really a small data set. And I can tell you, in the 80s, when the backpropagation algorithm came, it was sort of the solution. We could not only learn linear to classify linearly like we did in the neural networks prior to that. We could classify with 4 layers almost any type of data, but that was not the final solution.
Hmm. Given that you were initially working with Landsat and that had only 4 bands, why was it important to apply machine learning to analyzing the data?
It was important because, as I stated earlier, we were working with both multiple data sources and we were also working with complicated data. What was commonly used in the old days, for example, in remote sensing, pattern recognition or classification, you always had to model the classes that you have. And at Purdue, we were in Indiana farm country, so examples we had for statistical classifiers were for classifying corn and soybeans in the Indiana farm counties around Purdue, Tippecanoe County. But when we were looking at much more complicated data that we could not model them easily with the statistical models, we had problems. So using the machine learning makes things much easier. If you trust the labels of your data, you will come up with a solution or we can say a classifier that gives you more accurate results, and you don't need to worry at all about all the modeling.
Mm, mm. Aside from the limited data sources and content, what are the other limitations that impacted early machine learning?
There are several limitations. So the analyst must know how to use the algorithms, how you label the data and so forth. And that's something I worked on with the neural networks early on. The limitations are also the data itself. If you have limited data, a limited number of labeled samples, limited number of channels, the machine learning approaches may not be good.
I think our next guest would agree and would also add.
One of the biggest problems for Earth observation is the fact that you don't have enough data to train all these systems.
This is Dr. Paolo Gamba. He's a professor at the University of Pavia in Italy, where he leads the telecommunications and remote sensing laboratory.
People started to think how it was possible to use very small amount of data and therefore to use other approaches in order to multiply, let's say, the effect of this data.
Similar to Jón, Paolo has had a long and fruitful career in remote sensing, which has allowed him to witness the varied impacts and, of course, the challenges machine learning has brought to the field of remote sensing.
Then we move to deep learning, and many of the problems that we have for Earth observation are related to the fact that deep learning requires a lot of data, and therefore when you train this network, you have to be able to use the network in many different areas of the world by a small retraining of this network.
For those who aren't familiar with the term, what's deep learning and how is it different from machine learning?
Machine learning in general corresponds to all the algorithms which are able to translate the methodology that a human uses in order to understand some data and recognize, let's say, a building from a tree or a cat from a dog in an image, into a system which is an algorithm which is able to obtain the same result on a machine. So this is the general term of machine learning. Within machine learning, you have neural networks, which are a methodology and an algorithm that mimics the network of our neurons in our brain, of course, in a very basic way. The problem is that all this methodology requires to have some examples, like our brains require some examples in order to be trained. And therefore, all these methodologies are as good as the data that you use to train them. That's why for Earth observation, when you have an image of a specific part of the world, if you are not familiar with that specific part of the world, you are lost. And the same is true for an algorithm that has been trained to work on a specific area of the world, and then it's used on a different area of the world. What happens with deep learning is that these new methodologies try to extract features, so characteristics of the images, which are valid everywhere. Let's say, just to give you an example, colors or shapes or boundaries. Those are things that you have in every single image. But of course, the way they combine together give you the possibility to extract a specific type of object, a building versus a tree, or a cat versus a dog. But they're all made by color, shapes, and lines or boundaries. So deep learning is basically something that goes in that direction. The name deep comes from the fact that it's an improvement of neural network when we have multiple layers, which means multiple processing elements. That's the reason why we call it deep, as opposed to shallow, which means with very few elements, which is the original idea of neural network.
I understand. So, in the context of Earth observation, what have breakthroughs allowed us to do?
Well, the problem that we were trying to solve using Earth observation data were initially very basic one. Again, just to give an example, a map of a specific area where we recognize different type of element in the image. Now we are moving toward more complex problems, like I would like to extract the quantity of pollution which is in a urban area for every single point in a urban area. That's typically a very different problem than just mapping urban area. Therefore, the breakthrough using machine learning is basically the fact that we were able to use multiple data in order to solve more and more complex problems.
With the need to solve increasingly complex problems, scientists were compelled to push machine learning even further.
For a long time, machines couldn't compete against humans, but recently, because of the emergence of deep learning, machine learning is now outperforming the performance of humans. I think that's why it's really becoming essential for solving real-world problems in many different fields.
Coming up, Dr. Naoto Yokoya helps us understand the real-world implications of machine learning in remote sensing, particularly with respect to natural disaster emergency response. We also dive into one of the most fascinating things I learned about the impact of machine learning on remote sensing. All this right after the break.
Are you looking to make an impact in geoscience and remote sensing science? Then consider joining one of the Geoscience and Remote Sensing Society's technical committees. From environmental analysis to spaceborne imaging spectroscopy, each technical committee advances innovative research and technology in a specific field of remote sensing. By joining, you'll connect with a community of passionate researchers and professionals who are fostering important international collaborations and steering global research agendas. You'll also gain access to the latest news and state-of-the-art research in the field. Expand your network, enhance your career, and make a difference. Join a GRSS technical committee today by visiting grss-ieee.org/technical committees.
Welcome back. Today we're speaking to three different scientists about the history of machine learning in Earth observation. Dr. Jón Atli Benediktsson, rector and president of the University of Iceland, started us off by painting a picture of remote sensing before and just after machine learning entered the scene. As he described, machine learning allowed us to process much more complex data that modeling alone couldn't accomplish. It also allowed scientists to combine multiple sources of data, which led to a richer understanding of the phenomena being observed through remote sensing. Next, Dr. Paolo Gamba, professor and lead of the Telecommunications and Remote Sensing Laboratory at the University of Pavia, shared the most recent development in machine learning, the shift from shallow neural networks to deep learning. Paolo gave us a quick overview of the increasingly complex problems deep learning has allowed us to solve, as well as the challenges that have come along with it. The last voice you heard right before the break was Dr. Naoto Yokoya, lecturer at the University of Tokyo and geoinformatics unit leader at the Riken Center for Advanced Intelligence Project. As Naoto describes, machine learning has been an absolute game changer when it comes to being able to quickly interpret and act on remote sensing data. Why has machine learning been so integral to helping us solve real-world problems?
In my personal opinion, machine learning has become an indispensable technology in various fields because it can perform tasks that cannot be done by humans. For example, I'm from Japan, and Japan is full of disasters, and we are suffering from them. And the scale is actually getting larger and larger. So damaged area is becoming really, really huge. So if the damaged area is very small, visual interpretation or just going to the site is fine to get more accurate information. But when the damaged area is extremely huge, it's really, really not possible to analyze everything visually. If we do that, it takes 1 week or 1 month, and that's really not useful to support disaster response. So in that sense, automation is really the key. And also, in case of flooding, for example, flood extent map is a typical product. It's a kind of binary map, so where flood happened or not. After closely working with disaster management people, we figured out they need much more detailed information like inundation depths. So whether the water inundation depth was 50 centimeter or 3 meters, it means totally different damages to the buildings. Such information is really important, but such information cannot be obtained by traditional image processing using remote sensing imagery. And we work on combination of machine learning and numerical simulation and remote sensing to solve this problem. So machine learning is now enabling some sort of very variable tasks that were not possible by the traditional image processing techniques.
Well, machine learning has helped us increase our data processing capabilities, which is incredibly important for responding to disasters. In my view, one of the most interesting developments has been the way machine learning has led to more interdisciplinary approaches to solving real world problems. As I learned from Paolo, our use of machine learning is entirely due to cooperation between different disciplines. From this beginning, machine learning has led to increasing data fusion, both with respect to multiple sources of data as well as multiple scientific disciplines. So, you've shared breakthroughs in machine learning and how these breakthroughs impacted Earth observation. So, I'm curious, how were these breakthroughs achieved?
You know that science has this big advantage that it's one of the few things that when you share it, you multiply it, as opposed to losing something, you gain something else. And this is the fact. Machine learning and deep learning started as basically a methodology developed by computer scientists. So people working on algorithmic side, not the application side. But when we found out that using this new machine learning technology, it was possible to extract more information, it was possible to go beyond the analysis of a very small area of the world and try to extract information about a country or a region, meaning more than one country. Then it became evident that using remote sensing on the one side and machine learning on the other side, it was possible to extract information layers which are crucial for many people working on what is commonly called Earth system science. The advantage of remote sensing is that it covers the whole world. There are areas that are impossible to reach, like the middle of the oceans, for instance, and you can use satellite for that. And there are methodologies that now allow people to extract automatically or semi-automatically information about, let's say, the salinity of the water, which is a very important information for climate. Again, this is the reason why fusion, and here for fusion, I mean not only fusion of data, but fusion of different methodologies, fusion of different ideas, is the way we want to go, because this is the way that we can achieve more and more results.
Similar to Paolo, Naoto agrees that the data fusion aspect of machine learning is significant. And when I asked him about the future of machine learning in Earth observation, he took the data fusion concept one step further.
So, what I believe is important in the future is human-machine interaction, because, of course, human can give quite precise interpretation. It takes time, but interpretation result may be precise. On the other hand, machine learning can predict something very, very quickly with some errors. So the idea is, okay, why not to combine and why not to make collaboration between human and machines? So in case of disaster response, the machines can give an initial estimate. And then by looking at this and also looking at remote sensing images, and also we may receive some information from the ground, human can give a few annotations, and then machine can quickly fine tune the model and then make the prediction more and more accurate. So in this way, we can speed up and the accuracy is much better, and we can cover really, really large area. So I do believe in the future, such a human-machine interaction will be a really important topic.
So, in many ways, the future of machine learning is not just the fusion of multi source data or different disciplines, but fusion between human machine interactions. I really love this concept. So, in your opinion, what's the way forward with data fusion?
So that's a very, very good question, but also difficult question to answer. There is infinite ways of how to design architectures. One of the possible direction is to consider more physical mechanisms on the surface and also sensing system and embed such knowledge into the machine learning models so that we can somehow extract interpretable information. So in this case, when the model outputs something, model can also output some uncertainty, and maybe such interpretable model can tell us, okay, at this moment, I'm not sure about this part because this information is missing. So please add SAR image, for example. If the system can tell such information, we can know what to do and how to improve the results. So when we combine different data sets, there is always trade-off in spatial resolution or spectral resolution or temporal resolution. So if we compare just one pair of different data sets, there is always trade-off. And what I think is the ideal outcome is to achieve the best resolution, taking all the advantages from different multi-source data set. For example, in case of change detection, it should tell us the change at the highest temporal resolution. So all in all, that's something that I can imagine as the ideal outcome, having the best resolution from all the data.
Considering the future of such a powerful technology like machine learning is an exciting thought experiment. But as Dr. Jón Atli Benediktsson reminds us,
the analyst is really key. The algorithm is fine, but the scientist that evaluates the results is critical in obtaining the best results. We can overlearn if we are not careful. We can make mistakes. So my message to people regarding machine learning is that we are just starting. We will continue. There are plenty of opportunities to do things better in many ways, in terms of better algorithms, better results, more data. And I think there's a fantastic opportunity at the moment to analyze big data sets with machine learning and remote sensing.
Well, that's all for this episode of Down to Earth. Want to learn more about machine learning, Earth observation, and data fusion? Then reach out to the GRSS Image Analysis and Data Fusion Technical Committee at grss-ieee.org/technical committees. You can connect with Dr. Jón Atli Benediktsson by searching his full name on Facebook and LinkedIn, or by connecting with him at Jón Atli B on Twitter, Instagram, and Snapchat. Follow Dr. Paolo Gamba and his work on Twitter at EOUrban, and connect with Dr. Naoto Yokoya on LinkedIn or through his webpage at naotoyokoya.com. We have some fascinating episodes in store for you this season, so don't forget to follow us on Spotify and Apple Podcasts. And send some love to our sponsors at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Killam Media. And a special thanks to Fabio Pacifici and Keely Roth for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.